Hey guys, welcome back to my channel, and today we will look at a topic, chromatic polynomial for C4. Okay, chromatic polynomial. This is part 2. We have discussed about chromatic polynomials in part 1. You can check out that first before coming to this. We will look at a special case today. Special case, chromatic polynomial for a cycle of 4 vertices. Okay, this is a little bit different, and here you might do something wrong. Okay, so let us see at cycle on 4 vertices. Okay, so yeah, this is the cycle on 4 vertices. Now what people will, how I would do, if I don't know this special case, what will happen is I will do it normally. Suppose you have a set of lambda colors. Okay, so first node number 1, I can give it, color it using any of the lambda colors. Okay, node 2 has only one color has been used, it cannot get this color, so it will have lambda minus 1 choices. Node 3 also is connected to 2, so it can be colored using lambda minus 1 choices. Only one color, two's color cannot be used over here. And fourth one, uh, that we have over here, okay, one color from here, one color from here, right? It is adjacent to vertex 1 and vertex 3, so two colors it cannot be used using, so I can color it using lambda minus 2. But is this the right answer? The answer is no. This is not the complete answer. Here you are going wrong. Note over here, this is a very important case. See, this vertex number 1 and vertex number 3, there can be two cases. See, these two are not adjacent. That means these two, case 1 can be colored, 1 and 3 can be colored with same color, with same color. If it is colored using same color, say red, then vertex 4's adjacent vertices both are red colored. So it will have an option of lambda minus 1 colors, because only one red color it cannot use, otherwise it can be colored using any color. And second case is, this is case A. Second case B is when vertex 1 and vertex 3 are colored using different colors. Say vertex 3 is colored using a green color, not red color. Okay, we are coloring it using this green color. Okay, so that means now the fourth vertex is adjacent to 1 and 3, so it cannot use two colors exactly, so it has lambda minus 2 choices. Okay, so 1, we will just use 1 and 3 colored with different color, different color. Okay, so the chromatic polynomial for C4, it became, we'll go to the next page. Okay, so the chromatic polynomial for this graph. Okay, we'll write chromatic polynomial as a function C on this graph using lambda colors will be equal to lambda into lambda minus 1 square, lambda into lambda minus 1 square, uh, then lambda minus 2 plus lambda minus 1 into lambda minus 2 or lambda minus 1, right? So this is the polynomial, and can we convert it into a recurrence relation? So these two cases, case A and case B, can be rewritten as, we can rewrite it as, so suppose the first case when vertex 1 and vertex 3 are colored using the same color. Okay, so 1 and 3 are having the same color, so we can convert this, we can remove this, we can merge these two vertices into a single vertex like this. these two vertices can be merged into a single vertex like this, because we are coloring using the same color, right? So this is 1 and 3, this is 4, I guess, 4 and 2. So these two can be colored using the same red color, right? So this is case A. For case A, we can convert that C4 graph into like this. This is a similar coloring, right? And for the case B, we can write it like this. For the case B, where both vertex 1 and 4 are having different colors. So they are colored using different color. That means I can introduce an edge between 1 and 4. Then 1 and 4 has to be colored with different colors, right? 1, 2, 3, 4. So I can break this problem chromatic polynomial for a C4 using lambda colors can be broken into two smaller problems. The chromatic polynomial for this graph using lambda colors plus the chromatic polynomial for this graph with an edge added between 1 and 4 using lambda colors. So if we rearrange also for any graph, this graph, chromatic polynomial for this graph, okay, using lambda colors is same as we are bringing this portion of the equation to the left hand side. What we get, chromatic polynomial for edge removed, the diagonal edge removed, minus the chromatic polynomial for this, right? So for any graph with a diagonal, the chromatic polynomial for this graph will be same as the chromatic polynomial with the diagonal removed minus the chromatic polynomial when these two corners are merged together, right? That is equal to the chromatic polynomial for the graph minus this edge E, we will call this edge E, minus the chromatic polynomial when the E edge is coalesced into a single vertex. So G dot E, comma, lambda. That is chromatic polynomial for this graph with a diagonal edge E. So we can look at this, break this bigger problem into this smaller problem. Okay. All right. So remember these two things. So do not do this mistake wherever. So I will summarize what we looked while finding the chromatic polynomial for any graph. Always be careful if a vertex is adjacent to two vertices and these two vertices they are not adjacent, then there can be two cases. Either these two can be of different colors, so we will have lambda minus 2 choices for this fourth vertex, and they can be of same color as well, then we will have lambda minus 1 choices. So there are two possible cases over here. So be careful and do not make this mistake in exams. And happy learning. Stay tuned to this channel for more discrete math videos. And if you like this video, please share it with your friends, subscribe to my channel, and bye bye, happy learning.